Welcome to this advanced session on functional safety strategies. Today, we are diving deep into layer of protection analysis, or LOPA, and safety integrity level assessment. In the world of industrial process safety, managing risk isn't just about having good equipment, it's about having a quantifiable, defensible methodology for preventing catastrophic events. Whether you are a process engineer, an instrumentation technician, or a safety manager, understanding how to bridge the gap between a qualitative HAZOP and a fully quantitative risk assessment is vital. Over the next video, we will break down the methodologies used to analyze industrial risks and determine exactly how reliable your safety systems need to be to protect your people and your plant. Here is our roadmap for this session. We will start with the basics of functional safety, specifically looking at the IEC 61501 standard and the safety lifecycle. Next, we will demystify SIL concepts, understanding what those levels 1 through 4 actually mean in terms of reliability. The core of this video will focus on the LOPA methodology, providing you with a step-by-step process for analysis. We will closely examine IPL criteria, because identifying what is and what isn't an independent protection layer is often where teams get it wrong. Finally, we will look at a case study and some practical lessons learned to tie theory into practice. To understand LOPA, we must first agree on the definition of risk. In our industry, risk is defined as the combination of the frequency of a hazardous event and the severity of its consequences. No industrial process is risk-free. Therefore, our goal is not zero risk, but tolerable risk. This is a level of risk that is deemed acceptable by the organization or regulatory bodies, often adhering to the LOPA principle, as low as reasonably practicable. The difference between your initial, unmitigated risk and your tolerable risk is the residual risk, and our job today is to ensure that residual risk remains within safe limits using control measures. Functional safety in the process industry is governed largely by IEC 61511. This standard provides the framework for the design, implementation, and maintenance of safety instrumented systems, or SIS. It outlines the safety lifecycle, which is a systematic, circular approach. It begins with hazard identification, moves through risk assessment and requirement specification, and continues into operation and maintenance. The core principle here is risk-based. We do not apply safety systems arbitrarily. We apply them to reduce specific risks to an acceptable level. This requires multiple layers of protection, ensuring that if one fails, others are there to catch the hazard. Let us understand onion skin layer concept. In the world of industrial safety, we rely on a strategy called defense in depth, often visualized as this onion model. At the very core, we have the process itself. Moving outward, our first layers are designed to prevent loss of control. It starts with the basic process control system. If that wavers, we rely on alarms and operator intervention. And if human action isn't enough, the safety instrumented system acts as an automatic emergency shutdown. But if a hazard does escape these barriers, we rely on mitigation. This includes physical protection, like relief valves, followed by physical containment, such as bunds to catch spills. Beyond that, we have fire and gas systems to detect and suppress danger. If containment fails, we move to the final lines of defense. Plant emergency response to handle the situation on site. And finally, community emergency response to protect the public. By using independent, overlapping layers, we ensure that if one barrier fails, another is always standing ready to protect. We protect our facilities using a defense in-depth strategy, visualized here as 9 layers, starting with basic process controls at the center and moving outward to emergency response. However, no single barrier is perfect. Ideally, these layers would be solid walls, but in reality, they have weaknesses, like holes in Swiss cheese. By stacking multiple, diverse layers, we ensure that if a hazard slips through one gap, it is stopped by the next, preventing a disaster. It is crucial to understand that a SIF is designed to address a specific risk. It operates in a loop consisting of 3 parts: a sensor to detect the condition, a logic solver to make the decision, and a final element to take action. Let's look at the distinction between a SIF and the Safety Instrumented System, or SIS. The SIS is the entire bundle of hardware and software. The SIF is the function inside that system. A single SIS logic solver might host dozens of different SIFs. For example, SIF-001 might protect against high pressure, while SIF-002 protects against high temperature. Each function is independent in its purpose, even if they share the same logic solver. Crucially, each SIF is assigned its own safety integrity level, or SIL, based on how much risk reduction is required for that specific hazard. Let's apply this to the examples from the process industry provided in our slides. Consider a furnace. The risk here is an explosion if gas continues to flow without a flame. The SIF here is the flame failure loop. The sensor detects the loss of flame, the logic solver processes this loss, and the specific action, the SIF, is to immediately close the fuel gas emergency shutdown valves, ESDVs. Another example is a reactor. If cooling water is lost, the reaction could run away. The SIF recognizes the loss of cooling water and executes a specific set of actions, stopping the feed and depressurizing the reactor. In both cases, the SIF is the specific recipe for safety. If this bad thing happens, do that specific thing to make it safe. Let us look at another term often confused with SIF, SIS. Let's break down the anatomy of a SIS. It is composed of 3 distinct stages. First, the measurement stage, involving sensors like pressure transmitters or temperature gauges. Second, the logic stage, usually a programmable electronic system or PLC that processes the data. And third, the response stage, involving final elements like shutdown valves or circuit breakers. A critical rule in functional safety is independence. As noted in our text, the SIS must be functionally independent from the basic process control system, BPCS. Why? Because if the control system fails and causes an overpressure event, we cannot rely on that same failed system to save us. The SIS sits apart, watching silently, ready to take over only when the basic controls fail to maintain safe limits. In summary, while a SIF is the function or the verb, the SIS is the system or the noun. It is the physical sensors, the wiring, the logic solver, and the valves. It is the automated safety net of the facility. Whether it is closing a valve to stop a toxic leak or shutting down a turbine to prevent disintegration, the safety instrumented system is the engineered barrier that stands between a process upset and a catastrophic event. It is the embodiment of the phrase, fail safe. We have discussed the function SIF and the system, SIS. Now we must discuss the metric of their quality, the safety integrity level, or SIL. You will often hear terms like SIL 2 or SIL 3 thrown around in engineering meetings. But what does SIL actually mean? As defined in our slides, SIL is a measure of the probability to fail on demand, PFD. It is a statistical representation of the integrity of the safety instrumented system. Essentially, SIL tells us how much can we trust this safety loop. It quantifies the amount of risk reduction a system provides. The higher the risk of the hazard, the higher the SIL rating we need to mitigate it. The SIL classification table. Let's visualize the SIL classification table shown in our material. There are 4 discrete levels, SIL 1 through SIL 4. SIL 1 is the lowest level. It corresponds to a probability of failure on demand between 0.1 and 0.01. This offers a risk reduction factor of 10 to 100. This is used for lower risk scenarios. SIL 2 increases that reliability, offering a risk reduction factor of 100 to 1000. SIL 3 is for high-risk applications, requiring a system that fails extremely rarely, less than once in 1,000 demands. SIL 4 is the highest level, usually reserved for nuclear or catastrophic applications, offering a risk reduction factor of up to 100,000. It is important to note that as you go up in SIL, the cost and complexity of the system increase exponentially. In a SIL assessment, we are constantly comparing 2 numbers, the target SIL and the achieved SIL. The target SIL is determined by the risk analysis. It's how reliable the system needs to be to make the facility safe. The achieved SIL is calculated based on the actual hardware you bought, the sensors, logic solvers, and valves, and their architecture. If your achieved SIL is lower than your target SIL, you have a risk reduction gap. This gap implies that the residual risk is too high and the system design must be improved, perhaps by adding redundancy or choosing higher quality devices. Now, let's focus specifically on LOPA, Layer of Protection Analysis. LOPA is a semi-quantitative risk assessment tool. We call it semi-quantitative because it uses orders of magnitude rather than precise decimals. Its primary purpose is to determine if existing safeguards are sufficient, and if not, to calculate the required SIL for a safety instrumented function SIF. The methodology is disciplined. We identify the consequence, pinpoint the initiating event, identify independent protection layers, IPLs, and calculate the gap. It bridges the gap between qualitative HAZOPs, which rely on opinion, and complex QRAs, which rely on heavy statistics. When should you deploy LOPA? It is best used as a bridge. A HAZOP is great for identifying hazards, but it's subjective. A quantitative risk assessment, QRA, is detailed but expensive and time-consuming. LOPA sits in the middle. It provides a consistent, simplified, yet numerical framework. You use LOPA when the qualitative assessment in a HAZOP isn't enough to be certain about safety. It allows for a systematic evaluation of accident scenarios to objectively determine if the risk is tolerable or if further mitigation is required. Let's walk through the LOPA workflow. It is a linear process. Identify the consequence. What is the worst credible outcome? Fatality? Asset loss? Select the scenario. We assume the worst-case initiating event happens. Identify the initiating event. What causes the problem? A pump failure? A control loop error? Identify IPLs. What independent layers stand in the way of the disaster? Calculate risk. We do the math to see the unmitigated frequency. Determine the gap. Finally, we calculate the necessary risk reduction factor to hit our target safety level. The LOPA format typically follows a linear left-to-right spreadsheet structure designed to mathematically calculate the safety gap of a specific hazard. We start on the far left by defining the scenario. Here, we document the LOPA ID, the specific consequence, such as damaging a surge drum, and the severity category. Crucially, we list the initiating cause, like a control loop malfunction, and assign it a baseline frequency. Moving to the middle, we apply our credits. This section lists conditional modifiers, such as the probability of ignition or personnel occupancy. We then list existing independent protection layers, IPLs, including basic process control systems, alarms, and relief devices. Each of these is assigned a value that reduces the risk. Finally, on the right, we see the results. The sheet calculates the intermediate event likelihood and compares it to the max tolerable risk. The difference between them is the gap. The final columns explicitly state the required probability of failure on demand, PFD, the risk reduction factor, RRF, and the resulting target SIL needed to make the process safe. Let us see the details of each section one by one. The relationship between HAZOP and LOPA is a critical handover in process safety. Think of the HAZOP as the qualitative foundation. It identifies what can go wrong. It provides the raw data that feeds directly into the LOPA worksheet. As you can see in the mapping diagram, specific columns translate directly. The possible cause from the HAZOP becomes the initiating cause in LOPA. The consequence translates into the impact event, which helps us define the severity. Most importantly, the safeguards listed in the HAZOP are rigorously evaluated. We don't just copy them, we analyze them to see if they meet the strict criteria to be an independent protection layer, or IPL, such as a basic process control system or a relief valve. In this transition, we move from qualitative discussion to semi-quantitative math. This calculation allows us to identify the risk gap and determine exactly what safety integrity level is required to protect the process. To determine the tolerable risk frequency, we use a standard risk matrix that correlates severity with likelihood. First, look at the consequence side on the left. We rate severity from 1, being notable minor injuries, up to 5, which is catastrophic, involving multiple fatalities or massive environmental damage. Next, we map this against likelihood on the right. This ranges from A, an event happening once in 100 years, to E, an event occurring more than once a year. By intersecting these two axes, we find our risk ranking. For example, a major severity event, rating 4, that happens occasionally, likelihood C, lands us in the red zone at 4C. This categorization is critical because it dictates our target. The higher the risk ranking, the lower the tolerable frequency must be. This matrix directly tells us how rigorous our safety layers need to be to drive that risk down to an acceptable level. Once we rank a hazard on the risk matrix, say a major consequence occurring occasionally, we land in a high-risk zone like 4C. This ranking directly correlates to a target risk frequency. For a Category 4 event involving a potential fatality, our target might be 1 in 100,000 years, or 10 to the minus 5. This target frequency is the mathematical goal. It defines the gap between our current risk and where we need to be, telling us exactly how reliable our safety systems must be to close that gap. Next, move on to initiating event frequency. This is the table we refer to initiating even frequency. This data are from a variable reliable sources. For equipment failure rates, the ORIDA handbook is widely considered the gold standard, particularly for the offshore and oil and gas sectors. For the broader process industry, the most common references are the CCPS guidelines and the AICHE LOPA book. These are essential for finding typical, generic initiating event frequencies that are accepted by regulators. When we need deep reliability data for specific safety devices, we turn to the EXIDA Safety Equipment Reliability Handbook, or SINTEF's PDS data. Finally, for loss of containment specifically, we look to the UK HSE Hydrocarbon Releases Database, Energy Institute guidance, and API standards, specifically API 581 for piping and API 74 for process safety metrics. Using these recognized sources ensures your risk assessment stands up to scrutiny. Conditional modifiers are the external factors that determine if a hazardous event actually escalates into a specific consequence. Just because a release occurs, it doesn't guarantee a disaster. Certain conditions must be present. Here are the few examples that are commonly applied in LOPA. Probability of ignition, probability of occupancy or presence, probability of avoidance or escape, probability of injury, also known as vulnerability. Let's look at ignition probability. A flammable release only results in a fire or explosion if it finds a spark. To quantify this, we rely on the IOGP Risk Assessment Data Directory. The IOGP manual provides validated correlations showing that ignition probability increases as the mass flow rate of the release increases. Essentially, the bigger the gas cloud, the higher the chance it burns. Finally, we have occupancy probability. This calculates the likelihood of personnel being in the danger zone when the event happens. If an operator only patrols an area for 1 hour per shift, we apply a fractional credit, ensuring we calculate the risk based on actual exposure, not just theoretical worst-case scenarios. In the framework of layer of protection analysis, LOPA, the concept of an independent protection layer, or IPL, is the cornerstone of risk mitigation. An independent protection layer, IPL, is a safeguard capable of effectively preventing a specific hazardous scenario from progressing to an undesired consequence. It must be completely independent of the initiating event and independent of any other protection layers associated with that same scenario. While all IPLs are safeguards, not all safeguards qualify as IPLs. They must meet strict criteria for effectiveness and independence to be credited in a LOPA. If you like our video, please like, subscribe, and share. A safeguard is any device or measure that reduces risk, but to be credited as an IPL in a LOPA calculation, it must meet strict validation criteria. Typical examples of IPLs. We categorize IPLs into layers, moving from prevention to mitigation. Process design, inherent safety features built into the system. Basic process control system, BPCS, automated controls that keep the process within safe limits. Critical alarms and human intervention, where an operator is alerted and has sufficient time and means to act. Safety instrumented system, CS, automated emergency shutdown systems. Physical protection, devices like pressure relief valves or rupture discs. Post-release protection, mitigation measures like dikes, blast walls, or fire and gas systems. Emergency response, both plant and community response plans. In process safety, not every safeguard qualifies as an independent protection layer, or IPL. To be credited as an IPL in a layer of protection analysis, a device must meet 4 strict characteristics. First is specificity. An IPL isn't a catch-all solution. It is designed solely to prevent or mitigate the consequences of one specific hazardous event, such as a runaway reaction or a loss of containment. Second is independence. This is critical. The IPL must function completely separately from any other protection layers and, crucially, independent of the initiating cause of the danger. Third is dependability. We need to trust it. The design must account for both random and systematic failure modes, ensuring it does exactly what it was designed to do. Finally, auditability. If you can't prove it works, it's not an IPL. The design must allow for regular functional testing and validation to ensure the safety system is active and ready. Equally important is knowing what not to count. Testing procedures are not IPLs. They verify readiness, but they don't actively stop a hazard. Maintenance is not an IPL, it is a preventative activity. Alarms sharing sensors with the control system are not IPLs because they fail when the control system fails. Fire extinguishers generally aren't IPLs because they require manual activation and successful fighting of a fire that has already started. Be strict here. Counting bad IPLs leads to a false sense of safety. After the probability of failures of the IPLs are filled based on the reliable resources, now we perform the calculation. We take the initiating event frequency, say, once in 10 years. We multiply it by the PFD of our IPLs, say, a relief valve works 99% of the time. This gives us the intermediate level event likelihood per year. We compare this number to our tolerable risk criteria, say, once in 10,000 years. If our mitigated frequency is higher than the tolerable limit, the difference is the risk reduction gap. This gap tells us exactly how much stronger our safety instrumented function needs to be, usually determining if we need SIL 1, 2, or 3. Once LOPA identifies a gap, we design a safety instrumented function, SIF, to close it. The LOPA report essentially becomes the requirement specification for the SIF. If the gap is 100, we need a SIL 2 SIF, which provides a risk reduction factor of 100. We then define the sensing elements, the logic solver, and the final elements, like shutdown valves, required to achieve that rating. Finally, we verify the integrity of the design through calculation to ensure it actually meets the target set by the LOPA. Safety is nothing without documentation. The Safety Requirements Specification, SRS, is the Bible for the safety system. It takes the output of the LOPA and translates it into engineering speak. It defines the trip points, the response times, the safe state, and the maintenance requirements. This documentation ensures traceability. We can trace every valve and sensor back to the specific risk it is mitigating. This is essential for the lifecycle management and for verifying that the system remains safe 10 or 20 years from now. Even experienced engineers make mistakes in LOPA. The most common pitfall is overcrediting layers, claiming an alarm is an IPL when the operator is flooded with alarms and ignores it. Another is ignoring common cause failure, using two valves that share the same air supply. If the air fails, both valves fail. Finally, poor data quality, guessing at failure rates rather than using industry data. These errors result in calculating a lower SIL than is actually needed, leaving the facility exposed to hidden risks. In summary, LOPA and SIL assessments are the backbone of modern process safety. They provide a structured, defensible, and mathematical approach to deciding how much safety is enough. By rigorously identifying initiating events, validating independent protection layers, and calculating the risk gap, organizations can effectively mitigate operational hazards. This makes our industrial environments not just more compliant with standards like IEC 61501, but genuinely safer for the people who work there every day. Thank you for watching.